Welcome back to the deep dive. Today we are strapping in for a journey to the very edge of theoretical physics. We're tackling perhaps the single most mind-bending, counterintuitive idea to come out of the field in decades.
It's really the ultimate physics translator. It gives us a kind of roadmap that, cuts through decades of problems that were just computationally impossible.
We are talking about the anti-de Sitter conformal field theory correspondence.
Or as everyone calls it, CFT.
Right. And you, our listener, have given us some source material that is, well, it's dense, it's mathematically rigorous, and frankly, it's pretty breathtaking. Our mission today is to really get to the core of its proposition.
It is that gravity itself might not be fundamental in the way we've always thought.
Exactly. That it might be an emergent property of a purely quantum system.
That's the whole promise of the duality right there.
Yeah.
It proposes this perfect mathematical bridge. It links a theory that we understand pretty poorly, these difficult, strongly coupled quantum field theories.
Like the stuff deep inside nuclear matter.
Precisely. And it connects that to a theory we understand quite well, classical gravity, just in one higher dimension.
And the significance of this, it can't be overstated. It gives us an entirely new computational framework, this holographic dictionary we're going to talk about, to solve problems that were just thought to be intractable before.
Yeah, we're talking about getting real insights into the interiors of black holes, the fundamental nature of space-time itself. And even, the behavior of bizarre materials like high-temperature superconductors.
And it goes both ways, which is what's so powerful.
That reciprocal power is what makes it so foundational. You can translate a really knotty nonlinear quantum problem into what becomes a solvable, almost linear geometric problem.
So the complexity of something at strong coupling in 4 dimensions
Suddenly becomes the relative simplicity of a curved space-time in 5 dimensions.
Okay, let's unpack this. We have to start at the beginning with the origin story, because this correspondence isn't some, random algebraic coincidence. It came directly out of string theory. So if we're going to talk about string theory, we have to talk about D-branes. Can you kind of set the stage for us? What were the key physical ingredients that led to this whole conjecture?
Absolutely. So the whole idea really came from studying these objects called D-branes or Dirichlet branes inside type IIB superstring theory.
Okay.
So you have to picture space-time not as this smooth, empty void, but as something that's permeated by these extended objects.
Yeah.
A D-brane is essentially a surface, a hyperplane, where the endpoints of open strings have to terminate. They're stuck to it.
So if open strings are like tiny little pieces of thread, the D-brane is the fabric they're sewn onto.
That's a perfect analogy, yes. They're surfaces where the strings have what are called Dirichlet boundary conditions perpendicular to the brane, and that's where the D in D-brane comes from.
Got it.
And for this story, the most important object is the D3 brane. It's a structure with 3 spatial dimensions, and it's just sitting there inside the full 10-dimensional space-time of the theory.
And the real genius of the initial idea, as I understand it, was recognizing that you could describe these D3 branes using 2 totally independent theoretical frameworks.
That's the key. That is the duality. You describe the same physical object, let's say a stack of N of these D3 branes, all sitting on top of each other in 2 completely different regimes.
Okay, so what's the first way?
So first we have what's called the low energy limit. This is what gives us the quantum field theory side of the story.
Right.
If you look at this system at very low energy, all the long, heavy strings kind of detach and fly away. You're left with just the short, light strings stretching between the branes.
Okay.
And if we take the string coupling constant, which we call Greg's, and we make it really weak, basically sending it to 0, the interactions of these open strings effectively decouple from the gravity in the background space.
Yeah. So you isolate the physics that's happening just on the branes themselves. And what kind of theory do those interacting open strings create?
They create the dynamics of a gauge theory. Specifically for N-stack D3 branes, the theory you get is called N4 super Yang-Mills theory, or SYM with an SUN gauge group.
And crucially, that's a 4-dimensional theory. It lives on the brane.
Exactly. It has 3 space and 1 time dimension, just like our world.
Now, this N4 SYM theory is sort of famous in physics for being incredibly special. Why is that?
It's the closest thing we have to a perfect quantum field theory. Its beta function is 0.
Which means?
It means its coupling constant doesn't change no matter what energy scale you look at it with. The physics looks exactly the same at all scales.
And a theory like that has a special name.
It's called a conformal field theory, or a CFT, And that is the CFT side of the ADS-CFT correspondence.
Okay, so that sets up one half of the equation. We've got this perfect 4D quantum theory. Now, what happens if we look at the D3 branes from the other perspective, from the gravitational perspective?
Right, that's the supergravity limit. This is the other side of the duality.
Yeah.
So now, instead of weak coupling, we imagine the string coupling rings is strong.
Okay.
In that case, this stack of ND3 branes is a huge, massive source of gravity. It seriously warps the 10-dimensional space-time around it.
It's like a bowling ball and a trampoline.
A very, very heavy bowling ball. The solution to the supergravity equations for this setup is a highly curved geometry.
And then comes the famous Maldacena limit.
Exactly. Juan Maldacena's insight was to take a specific limit, a decoupling limit. You essentially zoom in on the region immediately surrounding the branes, the near-horizon region.
Okay.
And when you do that, the flat space-time far away just kind of splits off, it decouples, and what you're left with is a very specific, unique, curved geometry. It's called Hades S5 IS5.
Anti-de Sitter space in 5 dimensions times a 5 sphere, so that's still 10 dimensions total, but they're all curved and locked together in a very particular way.
Yes. And here, finally, is the grand conjecture.
The punchline.
The punchline is that the 4D Anhuis 4 SYM theory, which lives on the boundary of this space, is mathematically equivalent. It's the same thing as type IIB superstring theory, propagating through the 10D curved bulk of 8S5 by S5.
Okay, hold on. Conceptually, that sounds absolutely insane. How can a 4-dimensional theory possibly contain enough information to describe all the physics, gravity, strings, extra dimensions of a 10-dimensional theory? It feels like you're trying to fit a massive hard drive onto a tiny microchip.
That apparent absurdity is exactly why we call it holography.
Right.
And the bedrock reason we believe it, the first big piece of evidence, is the perfect match in their symmetries.
Ah, okay.
Both the 4D CFT and the 10D bulk theory, they share the exact same massive symmetry structure. It's the superconformal algebra SU2 24.
And where do those symmetries come from?
The D3 branes initially preserve 16 supersymmetries of a type called Poincaré. But when you take the special ADS limit, the curvature of the new geometry grants you an additional 16 so-called conformal supersymmetries.
And the total matches perfectly.
The total set of symmetries is identical on both sides. Every transformation you could do in the 4D world has a geometric counterpart in the 10D world, and vice versa. Without that perfect symmetry match, the whole conjecture would just crumble.
So symmetry gives you the theoretical reassurance, but the practical use, the magic trick, really comes from something called the large N limit, N being the number of colors in the SUN gauge group. Why is cranking N up to infinity so important?
It's the key that lets us trade these incredibly hard quantum field theory calculations for simple classical gravity calculations. We use what's called the 't-Hooft limit.
Right.
You let N go to infinity, but at the same time you hold a combination called the 't-Hooft coupling fixed. This coupling is lambda, and it's equal to GYM2 times N.
So you're increasing the number of internal degrees of freedom, the N, while at the same time you're proportionally weakening the fundamental interaction strength, GYM squared.
Exactly. Now, if you look at how the gauge theory organizes itself, the source material shows this really nicely. When you calculate the vacuum amplitude of the theory, L and Z, it naturally expands into a series that's based on the topology of 2D surfaces.
The math looks like drawings.
It does. The formula goes something like ln z is proportional to a sum of terms. N to the power of 2 minus 2 atts times some function of lambda. And h here is the genus, the number of handles on the surface.
That N to the 2 minus 2 at factor, that's the dead giveaway. Well, if H is 0, a sphere, the simplest shape, you get N squared. If H is 1, a torus, you get N to the 0, which is just 1. This looks structurally identical to the mathematics of closed string theory.
It is the defining link. That factor of 1 over n in the gauge theory expansion plays the exact same role as the closed string coupling constant, G's, in the bulk theory.
Ah, okay.
So when n is very large, 1 over n is very small, which means the string theory in the bulk is weakly coupled.
And string theory includes gravity.
Right. And Newton's gravitational constant in the bulk, Gn, is proportional to the square of that string coupling, Gs squared.
So Gn must be proportional to 1 over n squared.
And that's the moment of translation. That's the magic. As n goes to infinity, Gn goes to 0. This is the definition of classical gravity. Gravity becomes so weakly coupled that we can completely forget about quantum gravity effects. We can just solve the, relatively straightforward classical Einstein field equations in the 5D bulk.
That perfectly captures the computational breakthrough.
Yeah.
You connect a strongly coupled quantum theory, where the math just breaks down to a classical, weakly interacting gravitational theory in one higher dimension, which is just a geometry problem.
And the two limits are perfectly balanced. The duality connects the strong coupling limit on the gauge theory side, so when lambda goes to infinity, to the weak curvature limit on the gravity side. When lambda is large, the curvature radius of the ADS space, L, is also very large compared to the string length. The geometry is smooth and classical.
Here's where it gets really interesting. Because once you have the structure, you need the instruction manual. You need the dictionary. How do we actually translate physical concepts back and forth?
Right, the instruction manual is the holographic dictionary. It was formalized in what's known as the GKP-Witten relation, and provides this precise mapping between the two worlds.
It sounds incredibly technical, but the core idea is just, it's beautiful. The statistics and averages of the 4D quantum world are determined by the geometry and the dynamics of the 5D world.
That's it, exactly. The formal statement is that the generating functional of the CFT, which is a machine for calculating all of its correlation functions, is equivalent to the gravitational partition function in the ADS bulk.
So basically, the boundary conditions you set for fields in the bulk determine the observable properties of the quantum field theory living on the edge.
Precisely.
So if I have some physical quantity in my 4D field theory, what is its 5D counterpart in the bulk?
The central rule is this one-to-one correspondence. Every field that exists in the bulk, let's call it phi, in the ADS space, corresponds exactly to a local operator, let's call it script O, in the boundary CFT. And this correspondence is mediated by the boundary value of the bulk field. Think of it like tuning a dial. To measure the properties of a quantum operator O, you need to turn on some kind of external source field.
Okay.
In ADS CFT, the source you turn on is literally the value of the bulk field right at the boundary of the space.
Let's use the physical examples from the sources, because this is where the picture really snaps into focus for me.
Okay, good idea. Number one, the most critical example is gravity itself. The fluctuation of the bulk metric, Hunanu, the very definition of gravity in the bulk, is dual to the field theory's stress tensor, Tunu.
The energy momentum tensor.
Right, and this makes perfect sense. The stress tensor is the source of mass and energy in the field theory, and that's exactly what generates gravity.
Okay, that one tracks. What about something like electromagnetism?
So if the CFT has a conserved charge, like a global U1 symmetry, the bulk theory has to include a gauge field, a Maxwell field, AM. And that bulk Maxwell field is dual to the boundary's conserved current, Dramu.
And fundamental particles.
Well, massive scalar fields in the bulk, let's call them fake, are dual to what are called composite operators in the boundary theory. Things like the chiral primary operators, trace of x to the k, and the SYM theory.
So just to make this concrete, calculating how the energy and momentum are correlated in some strongly coupled 4D quantum fluid, a calculation that would be basically impossible with normal methods.
Becomes a calculation about how ripples, how gravitational waves travel through the 5D curved space-time metric. That is the operational insight. That's the power of the dictionary.
And it all seems to fit together so perfectly.
It does. I mean, you can even see it in the sealed structure. When you compactify the 10D supergravity down to 5D, you get 15 gauge fields. And that number, 15, matches precisely with the 15 conserved currents of the SO6R symmetry group of the boundary theory. Everything just clicks into place inside that shared superconformal symmetry.
Okay, now for what I think is the most elegant mathematical translation in the whole dictionary. The link between the mass of a bulk field and the scaling dimension of the boundary operator. How does the weight of an object in the 5D world relate to its properties in the 4D world?
It's a direct consequence of just solving the wave equation for fields propagating in that curved ADS geometry. For a bulk field phi in ADS-D plus 1, the formula is m squared L squared equals delta times delta minus d.
And for our case, we're in ADS 5, so the boundary dimension d is 4. So it's m squared L squared equals delta times delta minus 4.
Exactly. And delta here is the scaling dimension.
Which conceptually tells us how sensitive that operator, script O, is to changes in energy resolution, how it scales.
Precisely. So a large mass m for a particle in the bulk translates directly to a large scaling dimension, delta, for the operator on the boundary. This energy quantum number, delta, of the bulk field, is identified exactly with the scale dimension of its dual operator in the SYM theory.
Wow.
And you can check this. For those KK scalars we mentioned, phi-fic, Their mass squared is m squared equals k times k minus 4. You plug that into the formula.
That you get delta equals K, a perfect match.
A perfect one-to-one match. It's a crucial consistency check.
Okay, so let's nail down that calculation framework you mentioned earlier, the sort of dial versus reading analogy for getting expectation values.
Right. So you look at the behavior of the bulk field phi, very close to the boundary. The field can have two different asymptotic behaviors, two different fall-offs.
Okay.
The slow fall-off, let's call it phi 0, is the coefficient of the leading term near the boundary. That slow fall-off. That is the external source for your operator O. That's the input you fix.
That's the dial you turn.
Exactly. And the second, faster fall-off, phi 1, is proportional to the expectation value of O. That's the response of the system. That's the reading on the meter.
I see.
So by solving the classical equations of motion in the bulk with a fixed boundary source, the resulting field configuration tells you the expectation value. It gives you the observable property of the quantum system.
And we can link this back to the idea of renormalization group flow. The radial coordinate of the ADS space, whether you call it R or Z, acts as the inverse energy scale in the CFT.
Yes, this is a fundamental concept.
So as you move from the boundary, which is a high-energy UV cutoff, deeper into the bulk, you are physically flowing toward lower energies, towards the infrared, the IR limit of the quantum field theory.
The extra dimension isn't just some arbitrary space. It is the energy scale. The geometry itself is an encoding of the renormalization group flow of the quantum system.
Okay, so the N4 SYM boundary theory is this perfect scale invariant CFT. To talk about things like thermodynamics, temperature, entropy, we have to break that scale invariance. How do you introduce a finite temperature into this system?
You introduce a black hole.
A black hole.
In the bulk, the presence of a black hole is the geometric representation of temperature on the boundary.
That feels like a massive leap. Why a black hole?
Because black holes are fundamentally thermal objects. We know from Stephen Hawking's work that they have a temperature and they have an entropy.
Right.
So the gravitational dual of a strongly coupled gauge theory at some finite temperature T is the Schwarzschild 8s black hole, or SADS. For our 4D CFT, the dual geometry is in SADS black hole in ADS5.
And what does that black hole do to the geometry?
It naturally introduces a horizon at some radius, R+, and that horizon breaks the perfect symmetry of the pure ADS geometry, which corresponds precisely to breaking the scale invariance in the boundary theory.
So the black hole is a geometric thermometer.
It is. The temperature T of the field theory is identified directly with the Hawking temperature of the black hole, which is just a function of its size. T equals R naught over pi L squared.
Okay, so we have a thermometer. What about the ultimate measure of degrees of freedom, entropy?
This is where the holographic principle is really geometrically confirmed. Remember the Bekenstein-Hawking formula. The entropy S of a black hole is proportional to the area A of its horizon. S equals A over 4G.
Right.
Now, our black hole lives in the 5D bulk. Its entropy is supposed to measure the degrees of freedom of the dual thermal field theory, which lives on the 4D boundary.
But wait, in 4D physics, entropy is an extensive quantity, is proportional to the system's volume. But in 5D, the black hole entropy is proportional to its area.
And a 5D area is mathematically the same as a 4D volume. That dimensional mismatch and its resolution is the confirmation of the holographic principle. The information content of a higher dimensional volume is entirely encoded on its lower dimensional boundary area. The 5D gravity theory only needs its boundary to describe the full thermal properties of the 4D quantum fluid.
That is the ultimate realization of it. The geometry itself is the hard drive containing the quantum information.
And it all checks out. The entropy of the boundary field theory has to scale with n squared because that's the number of degrees of freedom.
And we already found that G must scale as 1 over n squared.
Right, which means the area entropy relationship locks the thermal physics into the exact same large N dynamics we established earlier. It's all self-consistent.
Okay, so for real-world systems, we often need to model things with a net charge or particle density. That requires a chemical potential. How do you get charge into this black hole geometry?
You follow the dictionary. We said a global U1 symmetry in the CFT, like charge conservation, has to be dual to a gauge symmetry in the bulk.
So you had a Maxwell field.
You add a Maxwell field, AM, to the bulk gravity action. You upgrade it to Einstein-Maxwell theory. And the resulting black hole solution is the Reissner-Nordstrom ADS black hole, or RNADS. It's characterized by both mass, for temperature, and electric charge.
And how do we read the chemical potential mu from this charged black hole?
The chemical potential is just the value of the time component of that bulk Maxwell field when you evaluate it at the boundary relative to the horizon. So this solution then describes a strongly coupled thermal system with a finite, non-zero charge density.
Which moves the model out of pure theory and into something you could actually apply to, say a plasma or a material with free carriers?
It does, but it also highlights one of the limitations of this classical gravity approximation.
How so?
If you take this RN80S black hole and cool it down to zero temperature, T goes to zero, you reach what's called the extremal limit. In this limit, the entropy of the black hole, S, remains a finite non-zero value.
Which violates the third law of thermodynamics. Entropy should go to zero at zero temperature unless you have some massive ground state degeneracy.
Exactly. The RN80S black hole has a macroscopic zero temperature entropy. In a normal quantum field theory, this would mean the ground state has an infinitely large degeneracy, which is problematic.
So what's the explanation?
The consensus from the source material is that this is an artifact of our large N approximation. At finite N, quantum effects would probably lift that degeneracy and force the entropy to zero. But in our simple, classical N goes to infinity model, the gravity solution is stuck with this residual kind of disturbing entropy. It's a good reminder that we are working with an approximation.
A crucial reminder that even the most powerful theories have their limits. Okay, let's pivot hard now into the real world. Where has this mind-bending geometric trick actually been put to work to solve physical problems?
Right, let's talk applications.
CFT is sometimes called holography for strongly correlated matter. So why are quantum critical points, these weird phase transitions you find in exotic materials, why are they such a good target for this technique?
Well, QCPs are inherently resistant to our traditional methods because they're characterized by strong coupling. The usual picture of quasi-particles just breaks down.
Okay.
But QCPs exhibit space-time scale invariance, which makes them kinematically linked to CFTs. So CFT offers this unique toolkit to describe the low-energy physics of these really hard-to-crack quantum materials.
But the conformal symmetry of pure ADS is isotropic, right? Space and time scale the same way. Real-world quantum critical points often have a more generalized anisotropic scaling.
That's the challenge, you're right. Instead of standard scaling, where t goes to lambda t and x goes to lambda x, many QCPs show anisotropic scaling, which is defined by a dynamical critical exponent, z.
Right, so time scales as lambda to the z times t, while space just scales as lambda times x.
Exactly. So if z is, say, 2, time flows quadratically slower than space.
And the logic of holography demands that we find a bulk geometry that reflects this slowdown of time.
We have to. The metric required to describe such a theory is a modified ADS metric. It successfully encodes that anisotropic scale invariance of the boundary theory.
But what are the geometric consequences of having z not equal to 1?
When z is not 1, the geometric throat of the space begins to distort quite drastically. And the sources point out that these geometries develop what are called Popti curvature singularities deep in the interior at what acts as the IR horizon.
So they're not as nice as pure 8S.
They're not. They're genuine, though generally mild, null singularities. This means an infalling observer would experience diverging tidal forces. It tells us that while the duality is robust enough to model these exotic symmetries, the resulting geometries often require a much more detailed understanding of the full string theory to ensure they're stable.
Okay, let's talk about one of the biggest success stories then, the quark-gluon plasma, or QGP. This is the strongly coupled fluid created when you smash heavy ions together at places like RHIC, and traditional QCD just failed to predict its behavior.
The QGP is the poster child for strong coupling. It's too hot and dense for our standard quantum field theory tools. But CFT provided a way to calculate a crucial property: the ratio of its shear viscosity eta to its entropy density eta.
And the calculation, which was done using the SADS black hole dual to the NF4 SYM plasma, it yielded a stunningly simple result.
Right. Eta over S equals 1 over 4 pi.
Just a pure number.
A pure universal number. The calculation itself involves looking at how classical perturbations, like gravitational waves, get absorbed by the black hole horizon in the bulk. But what made this result so revolutionary was its universality.
It holds for any theory with a simple gravity dual.
Any strongly coupled quantum field theory, whose gravitational dual is just described by the Einstein-Hilbert action by general relativity in the bulk.
Why did this result shock people so much?
It completely overturned decades of expectation. Weak coupling theories had suggested that as you increase the coupling strength, a fluid should get less perfect, and the ratio eta over S should approach 0. The ADS CFT result showed that in the infinitely strong coupling limit, the ratio stays finite and non-zero. It suggests that 1 over 4 pi is a universal lower bound on viscosity. Nature can't make a fluid that flows more perfectly than that.
And how did this compare to the experiments?
Experimental data from RHIC quickly confirmed that the QGP behaves as an almost perfect liquid. It flows with incredibly little resistance. And its measured viscosity ratio came out remarkably close to the predicted holographic lower bound.
Wow.
So even though the QGP is governed by QCD, not this perfect NG4-SYM theory, the fact that this universal lower bound was predicted using geometric methods. It provided a massive theoretical anchor for understanding all strongly correlated quantum fluids. It showed the power of geometry to describe quantum reality.
Let's move to another key application, modeling superconductivity. Holographic models try to describe things like high-temperature superconductors, which are still a huge mystery. This is sometimes called superconductivity without electrons.
Right, it's a model for systems where the charge condensation is driven entirely by strong interactions, not the traditional weak coupling mechanisms.
And how do you build the model?
You start with a charged RNADS black hole, which gives you the thermal density. Then you add a charged complex scalar field, phi, to the bulk. This scalar is the dual of the charged operator, O, whose condensation is going to cause the superconductivity on the boundary.
So what's the mechanism for the condensation? How does a black hole spontaneously cause superconductivity?
The key is in the geometry of the black hole's throat at low temperatures. As you cool it down towards a critical temperature, TKC, the near-horizon geometry of the RNADS black hole, approaches a very specific, highly curved structure, an ADS2 geometry.
Okay.
And within this ADS2 region, an instability develops. A scalar field that would be perfectly stable in normal ADS can violate something called the Bright-Loan or Freedman bound because of the extreme curvature of that ADS2 throat. And this violation forces the field to condense.
So the geometry of the black hole horizon itself triggers the superconducting phase transition.
Precisely. Below that critical temperature TC, the bulk scalar field develops a non-zero profile that extends all the way out to the boundary, even when you apply zero source. And this spontaneous non-zero profile is dual to the formation of a condensate on the boundary, which dynamically breaks the U1 symmetry and kicks off the superconducting state.
And when you calculate the resulting electrical properties, does it actually look like a real superconductor?
It exhibits the two necessary hallmarks. You use linear response theory to calculate the AC conductivity, which involves solving for small perturbations of the Maxwell field in the bulk. And you find two things.
What are they?
First, infinite DC conductivity. As the frequency omega goes to zero, the conductivity shows a distinct 1 over omega pole. That pole mathematically means infinite DC conductivity, the definition of a superconductor.
And the second?
An energy gap. The real part of the AC conductivity just vanishes for frequencies below a certain gap frequency, omega. And that's the signature energy gap you find in conventional superconductors, where you need a bit of energy to break up the Cooper pairs.
That's stunning. The model is just using classical gravity and electrodynamics, and it dynamically generates a quantum phase of matter that is usually incredibly hard to describe microscopically.
Yes, and the ability of ADA CFT to model these novel phases is why it's become such a huge resource for condensed matter theorists.
Okay, let's talk about some of the more philosophical and modern developments. We mentioned earlier that the radial coordinate of ADS acts as the energy scale for the quantum field theory. Let's expand on that profound connection between geometry and the renormalization group, or RG flow.
The RG flow is the process by which a quantum field theory changes its definition as you move from high energies, the UV, down to low energies, the IR.
Right.
So if you start with a pure CFT, which is a UV fixed point, and you deform it by adding some operator O, the theory begins to flow away from that fixed point toward a new theory in the IR.
And in quantum field theory, that flow is notoriously complex to compute.
But in the bulk, it has this incredibly elegant geometric description, domain wall solutions in ADA. When you deform the boundary, CFT, by turning on a relevant operator, one whose scaling dimension is less than the spacetime dimension, this corresponds to fixing the dual bulk scalar field to a non-zero value at the boundary.
And that non-zero source changes the whole geometry.
It forces the metric itself to evolve radically as a function of the radial coordinate. The solution is a domain wall, a region where the geometry transitions. It interpolates between one ADS geometry near the boundary, the UV fixed point, and a different geometry deep inside, the IR fixed point.
So the entire history of the system how its degrees of freedom are decoupling and changing as the energy drops, is physically written into the curvature of the fifth dimension.
Absolutely. And what's more, this geometric setup provides a gravitational realization of very deep field theorems. The source material notes this flow is consistent with the C theorem.
Which proves that our G flow is irreversible.
Right. The C theorem says you can never regain degrees of freedom you lost during the flow. A measure of the complexity of the theory, C, must always decrease. C of the UV has to be greater than C of the IR.
And the gravity gets this right.
The gravitational dynamics automatically ensure this irreversibility. The geometry simply cannot slow backwards. The domain wall in geometry encodes the thermodynamic and information history of the quantum system. It's a visual computational proof that the decoupling of degrees of freedom is a one-way street.
Okay, now for what is maybe the most modern and profound connection of all. Linking the geometry of space-time directly to quantum information theory, specifically entanglement entropy.
Entanglement entropy is this crucial measure of quantum correlation. It tells you how entangled a given spatial region is with the rest of the universe. And in strongly coupled systems, calculating it is usually impossible.
But in the holographic dictionary, this quantum mechanical property is calculated using a purely geometric rule, the Ryu-Takayamagi formula.
That's the cornerstone of this whole geometric information theory connection. To calculate the entanglement entropy, S sigma, for a boundary region bounded by some curve sigma, you have to look into the bulk geometry. And you find the minimal area surface M that ends precisely on that boundary curve sigma.
Minimal area is the key. It's like finding the shape a soap bubble would make if it were stretched across a wire frame, but sinking into a curved space.
Right. And the resulting formula is stunningly simple and familiar. It's S sigma equals the area of that minimal surface M divided by 4GN.
That looks almost identical to the Bekenstein-Hawking entropy formula for a black hole.
It does. The quantity that measures quantum correlation in the field theory is calculated using the area of a surface in the bulk gravity theory.
This formula seems to suggest that entanglement is what's actually knitting together space-time geometry.
That is the modern philosophical interpretation, that the geometry of the bulk emerges from the pattern of entanglement in the boundary field theory. If you could measure the entanglement entropy of a region, you could calculate the curvature of the space-time in the dimension above it.
It's the ultimate unity of gravity, geometry, and quantum information.
And it works. The RT formula has been used to reproduce known results for entanglement entropy in CFTs, providing overwhelming evidence that this D connection holds true.
So, what does this all mean? We started with D-brains and a mathematical curiosity, and we've ended up with this universal tool that gives us insight into the deep structure of quantum matter and the emergent nature of space-time itself.
I think the core power of ADI-CFT is that it provides a complete, non-perturbative description for certain theories of quantum gravity. It shifts the entire definition of what gravity is.
Right.
Gravity, geometry, black holes. They might not be fundamental forces or objects. They might be large-scale classical descriptions that emerge from the dynamics of quantum information in a lower dimensional system.
It requires a massive change in perspective. I mean, we are saying that our familiar four-dimensional space-time might be just a shadow, a hologram cast by a quantum field living on some distant, higher-dimensional boundary.
And, critically, this change in perspective gives us computational power. We've learned to use geometry, a field we master well, to solve the hardest problems in quantum field theory, like finding the viscosity of a perfect fluid or modeling condensation in strange materials. We've treated algebraic impossibility for geometric analysis.
And that brings us to our final provocative thought for you, the listener.
If the radial coordinate of ADS is indeed the physical length scale and energy scale of the field theory, the full history of the renormalization group flow, from the Planck scale all the way down to the macroscopic world. That means the entire physical history of a quantum system is mathematically encoded and contained in the specific, precise geometry of one extra emergent dimension.
So
if geometry encodes quantum history, what principles of quantum information are currently hiding in that geometric structure that we just haven't yet learned how to read?
a question that redefines what we even mean by space-time. Thank you for guiding us through this radical conjecture.
My pleasure.
That was our deep dive into the ADI-CFT correspondence. If the idea that 4D quantum information creates 5D gravity is still rattling around in your head, well, you're exactly where you should be. We'll see you next time.